Well, welcome back. Today we're going to talk about superposition. Our objectives for today is we want to be able to calculate the electric force using Coulombs Law. We want to be able to compare electric force with gravitational force. And we want to be able to apply the superposition principle to find the resultant force on a charge and to find the position at which the net force on a charge is zero. Coulomb's Law. Two charges near one another exert a force on another called the electric force. Coulomb's law states that the electric force is proportional to the magnitude of each charge and inversely proportional to the square of the distance. We're right back to that inverse square law, which we talked about when it came to the gravity, or the amount of gravitational force between two objects. And we said that was the biggest contributor. The farther they got away from each other, the smaller that force. It's the same way with the electric force. What I want to point out to you right here is if we take our gravitational force, I'm just going to write it up here at the top. These two equations become very similar. We have a constant here. We've got a constant here. We've got two magnitudes. The masses are the two magnitudes up top, and then down here for our electric force we've got two magnitudes, which would be the charges of the two objects, and then we still have this distance squared on the bottom. So they're set up the exact same way, except instead of talking about the gravitational force between the two because of the mass, we're talking about the electrical force between the two because of their charges. Coulomb's law. The resultant force on a charge is the vector sum of the individual forces on that charge. Now we may get to that in a few days. We're not going to be getting to that right away today. Adding forces this way is an example of the principle of superposition. And what that means is if we have one electrical force that's pushing an object this way, and another electrical force that's pushing this same object this way, then there is obviously this resultant electrical force. And we want to get to that, but we're not quite ready for that yet. When a body is in equilibrium, the net external force acting on that body is zero. And that would be that we had some charge here, and we'll say it was positive, and some charge here, some charge here. It's at equilibrium if all three of these, let's say, have a positive or plus 3 coulombs. Then this middle one would be in equilibrium as long as they were all the same distance from each other. Now we can change some things with this. Let's take this one over here to the left and now say it becomes 1 coulomb. Well, on the right it's got 3 coulombs, so it's going to have a much larger force pushing it away. And on the left side we're going to have this smaller force pushing it away. Well, what's going to happen is it's going to move to the left until it becomes in equilibrium. So the new position of this probably wouldn't be there in the middle. It would probably come over here closer to the one on the left and have a smaller distance between these two and a much larger distance. And because of that distance, this force would become smaller. Because of this distance, this force would become larger, and it would be in equilibrium, meaning there'd be no net external force, and it would stay put. All right, let's start to learn something here about this force then. We've got these 3 charges here, and what we really want to find is the magnitude and direction of the resultant forces on Q3. So what we're really talking about here is here at Q3, and one of the first steps we would go through is make yourself a little table that explains or gives you the force, the charge, and the distance they are from each other. And that's going to make life easier for you. Now, when we go to do this, you're going to use your equation. Force equals K times Q1, Q2 over the radius squared. It just dawned on me that up until this point, we have still yet to have given you what K is, what Coulomb's constant is. And what we find out here then is that Coulomb's constant, K, let's put it over here a little easier spot, K equals 8.9 times 10 to the ninth Newton meters squared per Coulomb squared. And as you can see, when you put this in, all of these are going to cancel out. The meter squared will cancel out with the meter squared on the bottom. Coulomb squared will cancel out because of the Coulomb squared on top. You'll be left with just newtons. So let's go ahead and plug this in here then. If I wanted to find the force on 2 due to 1, that would be 8.9 times 10 to the ninth, and then I'm going to put the two charges in. Q1 is 6 times 10 to the negative ninth times Q2 is negative 2 times 10 to the negative ninth, and then the radius, the distance between those two, would be 3 squared. And what that force turns out to be on 2 due to 1 is 1.2 times 10 to the negative 8th newtons. Now, at this point, actually I believe this should be a negative number, is the negative. That means that these two charges are going to be the force is an attractive force between the two. They're going to be attracted towards each other because one's positive and one's negative. Whenever you get a negative answer, that means the force is going to be attracting these two objects towards each other. As I've gone back and saw here, I'm actually doing the wrong ones, but it works the same way. Let's go ahead and find the force on 2 due to 3. Well, that's still going to be 8.9 times 10 to the ninth. And then charge 2 is still negative 2 times 10 to the negative ninth, and charge 3 is 5 times 10 to the negative ninth, and the distance between them is 5, so 5 squared obviously is going to be 25 there on the bottom. And after you've worked this out, you're going to get again a negative force, which means we have a positive proton and a negative neutron, or a positive charge and a negative charge, that is attracting each other. So there's an attractive force between these two objects. Now in this case, we've done the same thing again, except we've got some different numbers. What we want to do is find the magnitude and direction of the resultant forces on Q3. So we're going to find the force on 3 due to 2, and we want to find the force of 3 or on 3 due to the charge at 1. I've made our table. I've went ahead and put in all the information, and again we want to be finding the force on charge 3 due to 2, and I want to find the force on charge 3 due to charge 1. So those are the two that I want you to work out right now. So go ahead and hit pause and work those two out. Alright, a couple things we want to talk about here. The top one turned out to be negative, again, meaning that the charges were attractive to each other. And the bottom one, we have two positive charges, so they're going to be repelling each other. Now, which one of these two, and we're going to talk about that tomorrow, which one of these two is actually the larger force? Well, it's the bottom one, and we'll go into more detail about that tomorrow. The last thing I want to discuss here is the Coulomb's force is a field force. A field force is a force that is exerted by one object on another, even though there is no physical contact between the two objects. So field forces are not going to be touching each other. It would be, these two objects out in nature are not going to touch each other. So again, a field force is a force that is exerted on one object onto another object, but there's not going to be any physical contact. Hey, that's all for tonight. We'll see you tomorrow.